Hey everyone, welcome back. So we'll continue with probability today. So we'll first take a look at some of the definitions. So like experiments play a key role in many branches, like say physics, chemistry, and so on. They also play a role in statistics and probability. So how do we define a random experiment or a statistical experiment? So it is an experiment in which these three conditions are satisfied. So condition A, all possible outcomes are known in advance. So for example, if you're going to toss a coin, you know that the coin will either land on head or tails. So you know all possible outcomes. Any performance of the experiment results in an outcome that is not known. So if you toss a coin, you don't know beforehand whether it's going to land on heads or tails. You know all of the possible outcomes, but you don't know which exact outcome will materialize when you perform the experiment. The experiment can be repeated under identical conditions, right? So I can keep tossing the coin in a similar fashion over and over again. So it is convenient to associate with each such experiment the set omega of all possible outcomes. This is like the universal set, right? So this is a set of all possible outcomes of the experiment. So the elements of omega are called as sample points. Subsets of omega are events. Each 1 point set, so you take a subset, and if that subset contains a single point, right, a 1 point of that of omega, then it is a simple or an elementary event. Any event that is not simple is compound. So for example, say you toss a single coin, omega is head comma tail. These are all of the possible outcomes. So A is equal to, so there should have been a curly bracket here. Oh, let's see. So this is missing, and yeah. So if we have a set that contains H, that's A. So A contains a single point, right, from omega. So this is a simple event. B contains, right, more than 1 point. So B is not a simple event. So B is a compound event. Okay. Suppose we have a slightly more complicated experiment. We're tossing 2 coins. So you toss 2 coins, you'll observe a pair, right? So you have all of these possibilities. You can either have a head, tail, tail, head, 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 or tail, tail. So this is your omega or your sample space. And if you take any 1 point, now a point here is a pair, okay? Here it was either a head or a tail. A point here consists of a pair. So if you take A containing this pair, it's a simple event because it has a single element of this set. And B, it has 2 elements, therefore it is a compound event. So let's take a look at maybe slightly more interesting examples. So we have the following experiment. 10 radio sets are checked and the number of defective sets are noted. Okay, so we're looking at 10 radio sets and our experiment is observing the number of defective sets. So what are all the possibilities, or what is the sample space? And the second experiment is that we take a coin and we keep tossing it until head appears for the first time. So for the first example, right, this is what the sample space looks like. So remember, in each experiment, we are checking all of the 10 radio sets and counting the number of defectives. So the number of defectives can be 0, that's all of them are working fine. Or it can be, maximum number can be 10, that is all of them are defective. So omega takes all of these numbers between 0 to 10, right? So again, each experiment involves observing all of the 10 radio sets. Okay, so omega takes all of these integers. In the second one, you keep tossing a coin until the head appears. So you toss a coin, if the head appears right away, right, that's H. It's possible that you first toss a head, first toss a tail, and on the second toss you get head, so that's TH. and or the first two tosses results in tails followed by head, and then you get this. So these are all of the possibilities. So omega contains of all of these points, right? Remember, so note that there are infinitely many points here, right? Like you don't know when the head, like it's possible that you get a larger amount of tails, right? So it's possible that you have tail, 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 tail followed by head. So omega has infinitely many points or countably many points, and this omega here has 10 points. In the second experiment, if we chose to count the number of tosses required to get the first head, right? If that is what we were observing, then our omega would now change to these numbers. So we need 1 toss to get a head, 2 tosses to get a head, 3, and so on, right? So for each experiment, even though you're doing the same thing, your sample space might differ depending on what exactly it is that you are observing. So now that we know, right, so now with each experiment, we have associated a sample space, right? We conduct an experiment. Associated with it is a sample space. It is an event. That we also have an event. Event is basically a subset of the sample space, right? So now we are ready to define the probability of these events. So omega is a sample space, and for any event in this should have been omega, right? So basically, again, is that what it means is that A is a subset of omega. So we assign a number to this event, okay, so that it follows the following 3 axioms. So probability of A is greater than 0, that is probability of any event is non-negative. Probability of the universal set, that's omega, is equal to 1. So if you toss a coin, what is the probability that you observe a head or a tail? That is probability of a set containing H and T, that's going to be 1. And that makes sense, right? If you toss a coin, you have to either observe one of the two. You have to observe a head or a tail, right? So this definition makes sense. So if we have the sequence of sets, right, A1, A2, and so on, these are all disjoint sets, pairwise mutually exclusive. So what does it mean? It means that you take any 2 pair of sets, right? So AI, AJ, and so their intersection is 0 for I not equal to j. So that basically A1 intersection A2 is 0, A1 intersection A3 is 0, and you take each pair of sets, their intersection is 0. So if we take this sequence of sets, so probability of A1 union A2 union so on. So if we take the union of all of these sets, so probability of the union is equal to the sum of the probabilities. So this is an important rule. So if we have a bunch of disjoint sets, probability of their union is the sum of their probabilities. So if we have an experiment, right, we have omega, and if we have this p, right, this function p that satisfies these 3 conditions, then we say that p is the probability, right? So let's take a look at an experiment or an example. So a manufacturer has 5 identical looking computer terminals, and unknown to the manufacturer, 2 of the 5 are defective, and there is a particular order which calls for 2 of the terminals, right? And this order is filled randomly by selecting 2 of the 5 terminals. So what is the sample space in this experiment? So we have 5 terminals, 2 are defective and 3 are working well. So to list the sample space, so say we call the defective terminals as D1 and D2 and the good terminals as G1, G2, G3, right? And any single sample point. So what is the experiment? We're picking 2 terminals, right? Because we're filling the order and the order calls for 2 terminals. So we're picking 2 terminals at a time. So a sample point basically, so these are all of the possibilities, right? We pick D1, D2, or maybe D1, G1. and so on. So these are all of the possibilities, and thus the sample space has all of these 10 points. So the sample space here contains 10 points. Each point is basically this pair. So now A is the event that the order is filled with two non-defective terminals, right? So now we're interested in an event which has two non-defective terminals. List the points or sample points in A. So let's go back here. Two non-defective terminals, right? That means both the terminals are good. So we see here, right? E8 has both good terminals, E9 and E10. So if A is the event that has two non-defective terminals, then A contains these 3 points, E8, E9, and E10. Now we want to assign probabilities to these events in such a way, right, that those 3 axioms that I just mentioned are met. Okay, so how do we define probabilities on this? So remember that we're picking the 2 terminals randomly, right? So we had 5 terminals. We are selecting a pair randomly, and there were 10 possibilities, right? So there were these 10 sample points, right? And each of these sample point has an equal probability of getting selected, right? So if the manufacturer has an equal probability of picking either this one, this one, this one, this one, or any of these, right? So there are 10, each of them have equal probability. And remember, all of these probabilities have to sum to 1, right? Because probability of the universal set is 1. So it makes sense that we define this probability as of each sample point as 1 by 10. So probability of EI, right, is 1 by 10 for each of the, or for I going from 1 to 10. So this is reasonable. So let's find now. So now that we have defined probabilities for each of the sample points, let's find probability of this event A. And if you remember the third rule, so A contains of these 3 sets. These 3 sets are disjoint. So probability of A is basically probability of union of these 3 disjoint sets. And by the third rule, therefore, probability of this union is the sum of the probabilities. And we know that probability, each of these is 1 by 10. So therefore, the probability of A is 3 by 10. Okay. So what did we do? We had probabilities of E8, E9, E10. We know all of them are disjoint. So probability of A is just probability of this guy plus this guy plus this guy. Okay. So we're using the third axiom here. So that is all for this video. I will see you in the next one. Bye.